Good morning, and this is, I guess, the third video on floating point numbers, and we should be able to wrap it all up with this video right here. So let's consider the following, and also let's review with you a few things. First of all, this is video number 3, floating point numbers, FP numbers. I want to go back to something I gave you in the first video. Again, floating point numbers, the way we're going to talk about them, they're going to be represented as 32 bits. So they're a 32-bit quantity. And we said that this is broken up into 3 pieces. There's 1 bit over here, and that's the sign bit. It's very simple. 0 is positive, and 1 is negative. Then there are 8 bits over here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and this is called the exponent. And we need to explain that shortly. And then over here, there are 23 bits here, and that's called the mantissa. And we're ready to see now how we put this all together. So I want to start off with a simple example here, and I'm going to say express minus 19.375 as a 32-bit floating point number. Well, the first part is easy. I see this minus sign right over here, so that tells me that over here there's going to be a 1. Now what I want to do is I want to express 19.375 as a normalized floating point number. And let's remember, well, 19 is equal to 16 plus 2 plus 1. And 0.375, I hope you all know, 0.375 is equal to 3/8. So 3/8 is equal to 1/4 plus 1/8. So this is 16 plus 2 plus 1 plus 1/4 plus 1/8. So if I wanted to go ahead and express this in binary, that's a 16, that's an 8, that's a 4, that's a 2, that's a 1. That got me the 19. And then I put a point. There are no halves. There is a 1/4, and there is an 1/8. And that is times 2 to the 0. Now that's not normalized. Remember, normalized, I have to have exactly 1 non-zero digit to the left of the decimal point. So I've got to move this decimal point from here to here. Well, if I move it over 1, that would be times 2 to the first, times 2 to the second, times 2 to the third, times 2 to the fourth. So this is equal to 1.0011011 times 2 to the fourth. This is now normalized. Okay? So now the question is how does this fit into the remaining bits up here? Well, it turns out the mantissa is the easy part. The mantissa stores everything to the right of the decimal point. And this is going to be where most people will make mistakes in converting into the 32-bit quantity or interpreting the 32-bit quantity. This does not get stored, okay? We always assume that there is a 1 to the left of the decimal point. Remember, whenever we normalize things, we said we want to have exactly one non-zero digit to the left of the decimal point. Well, if we're working in binary, there is only one number that could be, and that is a 1. So far now, if I were to come over here and say, what does minus 19.375 look like? I can describe a large portion of it. Okay, over here in the sign bit, there's going to be a 1. Why is there a 1? Because this is a negative number. Now I've got the exponent, which we said is 8 bits. 2, 3, 4, 5, 6, 7, 8. So there are 8 bits here. And then we have to store the mantissa. Well, the mantissa is 23 bits long, and we just start copying these over here. So it's going to be a 0, and then another 0, and then a 1, and a 1, and a 0, and a 1, and a 1. Now that's 1, 2, 3, 4, 5, 6, 7 bits, but the rest of it are just all zeros to there. Okay? So the tricky part now here is how do I express the exponent? And here's what I want you all to remember. If I have 8 bits available to me here, 1, 2, 3, 4, 5, 6, 7, and 8. This is 8 bits. Okay, that as an unsigned integer in 8 bits, I can go from the number 0 up to 255. Now, what we do for storing you have to remember that we're storing in here potentially a positive exponent, as we saw over here. There's 2 to the 4th, but it could be possibly a negative exponent. And the trick that they use is they use something really weird. I'm telling you the name, but you don't have to remember it. It's called XS 127 code. And basically what they're saying is that if you want to store an exponent of 0, you would put in 127. If you wanted to store an exponent of 1, you would put in 128. If you wanted to store an exponent of 2, you would put in there 129. On the other hand, we'd go in the other direction for the negative exponents. If I want to put in there 2 to the minus 1, I would put in there 126. 2 to the minus 2 would get me to 125. And you can see over here that what I'm able to do is if I were to go all the way up to 255, that would actually be, if I were to go all the way up to 255 over here, that would actually be an exponent of 2 to the 127th. And if I were to go all the way down to 0, it would be an exponent of minus 127. So what's going on over here is we have to store an exponent of 4. So what that means is if I have to do an exponent of 4, well, 2 to the 3rd would be 130, and 2 to the 4th would be 131. The reason why it's called XS 127 is I would just go 127 plus 4 gets me to 131. So that's what I need to store in the exponent field. Now 131 is equal to 128 plus 2 plus 1. So the exponent for this number should be 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it should be 128, 0, 0, 0, 0, 0, 2, 1. This would be the exponent for the number that we were working on. Let me see if I can find it. It's right over here. So what I need to put in here is just the following. 1, 0, 0, 0, 1, 0, 0, 0, and then it needs to be 0011. Okay, let us just recall that this number here is 131, which means we should interpret this as being 2 to the 131 minus 127, which is 2 to the 4th. So this is expressing the exponent right over here. This over here is expressing the mantissa, what is to the right of the decimal point. By the way, suppose you were told to express it as a 32-bit floating point number in hex. Well, then what I'd have to do is I'd have to come over here and break this up into 4s. So there's 1, 2, 3, 4. So that would be 8 plus 4 is 12, which is a C. So that takes care of 1, 2, 3, 4. Then I've got 1, 2, 3, 4. That's a 1. So that is 1, 2, 3, 4. Then that is 1, 2, 3, 4. That looks like an 8 plus 1 is a 9. 1, 2, 3, 4. Then it's 1, 2, 3, 4. That's 8, 9, 10, 11 is a B. And then it looks like it's 0 for the rest of the way. Now this is 16 bits, 20 bits, 24, 28, 32. So this number right here, C19B0000, is minus 19.375 as a 32-bit floating point number in hex, just like that. Why don't we try another one? Why don't we express 73.75 as a 32-bit floating point number? So let's figure this out. 73 is 64 plus 8. 64 plus 8 is 72, plus 1 is 73, plus 1/2 plus 1/4. So that's equal to, that's 64, then that's a 32, then that's a 16, then that's an 8, then that's a 4, then that's a 2, that's a 1, that's a 1/2, and that is a 1/4. And this would be times 2 to the 0. Okay, now we need to normalize. So if I move it over here, that's 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th. So it's 1.001001111 times 2 to the 6th. So 6 plus 127 is equal to 133. So I need to put this into my 8 bits. So I'm going to come over here. So for the sign bit, it's a positive number, so I'm going to put a 0 there. Then I need to put 133 here. So first of all, that's 1, 2, 3, 4, 5, 6, 7. There are my 8 bits for the exponent. 133 is equal to 128 plus 4. That would be 132 plus 1. So here's 128. This is 1 over here. That's 2. This is 4. And now here is my mantissa. 0, 0, 1, 0, 0, 1, 1, 1, and then there are zeros the rest of the way. And again, if I were asked to express this as hex, I would come over here. Let me make this a little bit easier to see. I'm going to change my color. So I'm going to break this up into 4. 1, 2, 3, 4. That didn't work. I thought, why am I not getting a different color here? Sorry about that. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. The rest of these are all zeros. So this over here is a 1, a 2, 4. This is a 2. This is an 8 plus 1 is 9. This is 1, 2, 3, 4. That's a 3. This is an 8. And then it looks like the rest are zeros. So the answer in hex would be that right there. Okay? We're going to do a couple more. Ah, what happens if I start writing? Ooh, that's kind of fun. Why don't I come over here and why don't I express 11 over 64 as a 32-bit floating point number. That's quite a color there. Maybe I should change this back. I'm not sure I know how to. Let's do. Yeah, that's easier on the eyes. Express, what was it? 11 over 64. As a floating point number. Now note that 11 over 64 is equal to 1/8, which by the way is 8 over 64, okay, plus 1/32, which is 2 over 64, plus 1 over 64. Eight, 9, 10, 11, that's where I get the 11. So first of all, if I was going to write this, this would be 0 point, okay? There's a half, there's a quarter, there's an eighth, there's a 16th, there's a 32nd, and there's a 64th, and this is times 2 to the 0. But now what I have to do is I have to normalize this, and we recognize now what I need to do is I need to move this decimal point 3 points to the right. So this is actually equal to, 0.01011 times 2 to the minus 1. And this is equal to 0.1011 times 2 to the minus 2. But that's equal to 1.011 times 2 to the minus 3. Okay, and now this is normalized right over here. So again, what I need to do is I need to come over here and the first thing I do is the sign bit. The sign bit is 0 because this is a positive number. Then I've got 1, 2, 3, 4, 5, 6, 7, 8. And then I've got my mantissa here, 0, 1, 1. Remember, I don't store this leading 1. So I come over here and I put a 0, 1, 1, and then it's just zeros the rest of the way. And now what I need to do is I need to figure out how to express this minus 3. Well, remember, 127 corresponds to a 0. 126 would correspond to a minus 1. 125 would correspond to minus 2. Whoops, 127, 126, 125, I've got it. 124 would correspond to minus 3. So what I need to put in here is the number that corresponds to 124. Well, let's see if we can remember. 127 would be 0, 2, 3, 4, 5, 6, 7, 8. That's 127, and basically I've got to get rid of 3. That's 3 right over there, so it'd be 0, 2, 3, 4, 5, 6, 7, 8. That looks like that should be 124. If I'm not sure, it's 1 plus 2, so that's a 4. That's an 8, that's a 16, that's a 32, and that's a 64. 32 and 64 is 96. 96, this would be 112, that would be 120, that would be 124. So I come over here and I put in a 0, 3 ones, 1, 2, 3, and then I get 1100. 1100, like that. If I had to convert this to hex, I would come over here and I would go from here to here, and I would go, well, that's a 3, and then I would go 1, 2, 3, 4, and it looks like I see 1110. That would be an E. Then I would come over here and I'd go 1, 2, 3, 4, and that looks like a 3. And then it looks like I've got zeros the rest of the way. So there's a 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. So the answer in hex would be that right there. Okay? Okay, I just paused it. I hope I'm recording again. I want to finish up with one more example. Suppose I'm given the following. Suppose hex 4, 0, A8, 1, 2, 3, 4. And remember, whenever we precede something by 0x, that's an indication that what follows is hex. So this is 1, 2, 3, 4, 5, 6, 7, 8. 8 hexadecimal digits times 4 bits. This is a 32-bit quantity. So I say, suppose that this number is a 32-bit floating point number. And I say, find the decimal equivalent. So what I have to do is I have to write it out in a binary. So 4 is going to be 0, 2, 3, 4. Then there is a 0, 1, 2, 3, 4. Then there is an A. Let's see, A is 10. That's going to be 1, 0, 1, 0. Then there's an 8, which would be 1, 0, 0, 0. And then it looks like I've got a bunch of zeros all the way to the end. Now I package this up into the format of our 32-bit number. I see that it's positive. 1, 2, 3, 4, 5, 6, 7, 8. So I can see, looking at this number over here, that's 128 plus 1 is 129. So remember, 127 corresponds to an exponent of 0. 128 corresponds to an exponent of 1. 129 corresponds to an exponent of 2. So this over here represents 2 squared. And now I come over here, and here's where people make the big mistake. I've got to be very, very careful here. This is the mantissa. So remember, what this is this represents everything to the right of the decimal point. So this is 0, 1, 0, 1, and then a bunch of zeros. But here's what people forget. Remember, there's an implied 1 that isn't stored. So it's really this number right over here. So this number is really, well, that's a 1 plus, that's a half, that's a quarter, that's an eighth, that's a 16th. So this is equal to 16 over 16 plus 4 over 16 plus 1 over 16. So that's 16, 20, 21. That's 21 over 16. So this number here, this entire big number here, is really 2 squared times 21 over 16. Well, 2 squared is 4, so this is 4 times 21 over 16. And I go ahead and I cancel. Okay, so I cancel the 4 and I cancel the 16 and it becomes a 4. This is 21 over 4, which is equal to 5 1/4, which is equal to 5.25. And either one of these answers is fine. I don't particularly care. But this is converting a 32-bit floating point number, finding the decimal equivalent. So this is going the other way. And again, the place where people make the big mistake is in forgetting this number here, because this number here does not appear anywhere here in this 32 bits. And that's the story. I'm going to pause for a second while I look up some exercises in the book that you should do.